Welcome back to ECE 441A, 541A. There's quite a list of announcements. Homework number 3 is due today. There is a technical elective information session if you're an undergraduate student, or I guess a graduate student could listen to some of that because most of our classes are dual numbered. So if you're interested in that, that will be Wednesday night at 5:30 p.m. in room ECE 530. I think that's what's... Will I be... What? I'm going to be presenting the technical elective session, info session on that time, or I think I am. Who knows if I'll be there or not. I may... But it's going to be recorded, so you'll be able to have access to that, or I'll try to post that. Homework number 4, I will try to make that available today. I don't want you to get confused with that and homework number 3, so we'll give the hints on homework number 4 on Wednesday's class so that you can maybe more quickly get through homework number 4, and you can see that we have those two homeworks 4 and 5 due prior to exam number 2, and exam number 2 is a week from Friday. The following Friday, we don't have class. It's engineer's breakfast. That's the 28th. And the following Monday, lab number 2 will be due. Here's what we want to do today is to recap and complete our coverage of design specifications. That's chapter 5. Then someone after class said, you didn't give us the answers for the matching quiz. So we'll talk a little bit about the matching quiz now that we know maybe what a little bit more, have a little bit more insight into how that works relative to the design specifications. And then we will get into a discussion of another trade-off in control, and that's settling time and steady state error. Settling time is transient behavior. How quickly does your system settle? And steady state error is what happens when you reach steady state, the accuracy. And we'll talk a little bit about that, and we'll do that settling time. I'll see if you can come up with the settling time answer now that we've worked through design specifications, and we'll do a think, pair, share for you to get the answer, and then you'll pair up and compare answers, and then you'll share them back as a class, hopefully with the same consistent answer. Let's recap on the design specifications, and we really are talking about 3 different things, and these deal with transient behavior. We have a 2% settling time, we have a peak time, and we have a percent overshoot. Those 3 design specifications we want to become very comfortable with. And relative to the settling time, if I say settling time, what should you be thinking, or what mental image should you be envisioning if I say settling time? Should you be thinking about a line? And if you are thinking about a line, where is that line in the S-plane, and how does it orient itself in the S-plane? We're going to have a horizontal line, a vertical line, and an angular line. And when I say settling time, I want you to really start to be thinking about a particular line and maybe being somewhere in the complex S-plane relative to that line. So if I say settling time, which now we're talking 2%, that's 4 tau, or 4 over sigma, if I now said put a line, now it's like pin the tail on the donkey, but now we're pinning the line on the S-plane. So you walk up there, and hopefully you're not completely blind, but you can now figure out where do you put a line. Is it horizontal, is it vertical, or is it an angle if I say settling time? Did everyone get that? This is not a filtering class, but you know how to filter, and hopefully you have the correct filter. You guys usually do low pass and high pass, not correct and incorrect filtering, right? But what's the correct filter? How many think it's vertical? Show of hands. How many think it's horizontal? Show of hands. How many think it's angular for settling time? Okay, so we have a mix, which is not what I was hoping. But if I now say settling time, what's that sigma telling you? Sigma is, I hope, making you think that you now have this distance sigma and you want to be over here in the complex S-plane to locate your dominant poles. So when I say settling time, you should be thinking vertical line, and you can push that vertical line left or right depending on how fast you want your system to settle. If you want your system to settle quicker, where do you want that line? Further right or further left? If you want a fast system, meaning the settling time is short, T sub S is tiny, do you want that line to be closer to the imaginary axis or further away? Further away. You want to push that so that you have a bigger negative number, e to the minus 10t versus e to the minus 1t. So, faster system, smaller T sub S, shortening time implies what on sigma? Smaller or larger sigma? Where sigma now I'm meaning is the absolute value. We know it needs to be in the left half plane to be stable. So I'm asking one of two questions, smaller sigma or larger sigma? I think I just told you the answer, didn't I? So larger. That's one of our three design specifications. Oh, process of elimination. Now you have a better chance of what might be expected for peak time. If I now say peak time, you need to be thinking about a particular line, vertical, horizontal, or angular, and what do you think it is for peak time? So now you're getting a little bit more confident because we've already eliminated some. What? You know what line I was talking about? Okay. So now where do you want to be if you want a, so now we're thinking of horizontal line. And where do you want to be relative to that horizontal line, below it or above it, if you want a quicker or a faster time to peak? You can look at your time to peak equation and say, oh, how do I adjust omega sub d to make T sub p smaller? So you need to make omega sub d bigger, don't you? You want a larger imaginary component on your complex poles. You want to be up here, and I'm not going to show its twin, but you have the opposite or its reflection across the real axis for its complex conjugate. But you now are looking, did I put another blank here? So if we want a quick start, so a peak time is how fast do you get to that peak? That's sort of a quickness of your response. If you want a quick start, what do you want to do with omega sub d? Do you want to increase or decrease omega sub d if you want a quicker start? You want to go up, don't you? You want to make it bigger. So you want to increase omega sub d. Those are the two design specs that we covered last time. Let's now talk about the third design specification, which is percent overshoot. And from before, we had this response equation, y of t, which was 1 minus 1 over the square root of 1 minus zeta squared, e to the minus zeta omega sub nt, sine of omega sub dt plus theta. And maybe you have that memorized, maybe not. It's in your Laplace transform tables probably with your Laplace transform pairs if you're inverse Laplace transform. But if we're looking at the percent overshoot, what piece, well, where are we going to end up? What's our final value for the output? If this is our expression for the output, what's our final value? You should be able to just get, right? Because we have a transient, but that goes away, and what's left is the 1. Our final value is 1. What are we interested in if we're interested in percent overshoot? If we know our final value, what piece of this y of t expression do we want? Or where do we want the output at what particular time for the percent overshoot? We want its biggest point, don't we? We want the percent overshoot. We want to know when is y getting it to its maximum or at its peak, time to peak. We're evaluating this expression at the time that it peaks. We now are looking at y of t when t is equal to t to p, t sub p, and that's pi over omega sub d. And the textbook actually calls that max p t. Don't ask me the notation, but just think time to peak. P and t are in there somewhere. So peak time, m sub peak time. So what's the maximum value at the peak time? And if you plug in t equal to pi over omega sub d, and we know that the relationship between omega sub d and omega sub n has this square root of 1 minus zeta squared in it, and the sine of two angles will eventually boil down to sine of pi plus theta, and you'll do the trigonometric relationships, and that will all fall out, and you'll end up with a sine of theta, which is this square root of 1 minus theta squared. Those will cancel, and it will all become a little cleaner, and you now have 1 plus e to the minus zeta pi over the square root of 1 minus zeta squared. In the book, they label as m sub p. So we now have m sub p more than 1 to make up m sub pt. And what is our percent overshoot? In general, if somebody simply gave you a time domain formula or picture of your trajectory of your time response for the percent overshoot, you would be doing y, if you call it peak, or y final, let's call it y peak, minus y final over y final times 100%. That's how you would compute the PO, the percent overshoot. In our case, in this particular way that we have now parameterized our system, where it has a DC gain of 1, what's our y final in this y of t expression that's now at the top of the screen? That's the 1 that we talked about. And we've just computed the y peak. So if we take y peak, which is 1 plus mp, minus 1, we're going to be left with mp. And we're dividing by 1, so that the percent overshoot in this particular example, or in our particular case, is now m sub p times 100%. Or if we look at the percent overshoot over 100, that's m sub p, which is that term that involves this exponential. That's now this e to the minus zeta pi over the square root of 1 minus zeta squared. This is now the relationship between the percent overshoot and our damping ratio zeta. And we now have a lot of algebraic skills or algebra skills. We can invert that. We can now solve for zeta in terms of PO. We can take the natural log of both sides. And now we get rid of that exponential. And now we just have a ratio of zeta terms. We can do some more algebra. And what pops out is this expression for the damping ratio. It's now the natural log of PO over 100 squared over pi squared plus that same quantity, ln squared of PO over 100. And we need to take the square root of that. So you can now compute this. If somebody gives you 20 for a percent overshoot, you plug in 20 and out will pop zeta. You plug in 10. If you say, I want a 10% overshoot, you plug in 10 for PO and out will pop zeta. Is that a linear relationship between zeta and PO? Do you have zeta is equal to alpha PO? No. You have some square root, natural logs, division. It's a nonlinear relationship, and here in figure 5.7 of the textbook, if you look at this first curve that's going down from above, that's your percent overshoot relationship relative to zeta. And you now need to be, when somebody says percent overshoot, and you have a second order system, you want to be envisioning this curve. If somebody says that you want a 10% overshoot, you would then say, oh, you want a 10% overshoot. You would come over until you intersect with that green curve, and then you would come down and you say, oh, you need a damping ratio of about 0.6. Somebody says, oh, no, I want a 5% overshoot. Then you would come over here and you would say, oh, I need a damping ratio of 0.7. Do you get the idea? On an exam, you can have this figure and you can quickly, you don't have to punch that in, so if you don't have it stored in your calculator, or if you don't have storage in your calculator, if you have 4 functions, you can pull this out and simply find your zeta from your percent overshoot. And that's fine. Our answers are not all going to be the same. I think you're getting that feel in this class. You're probably a little uncomfortable when you come in and you go, but my third significant digit isn't the same as yours. Really? We're doing a lot of rules of thumb in this class, so if you're within a few percent, we're pretty good. So if I now said I want a percent overshoot of 50%, what's your zeta value that you're looking for? You know how to use this curve, right? So you say, oh, 50%. Now you need to be about 0.22, don't you? Hopefully you're getting the idea. So that now when you see somebody or somebody's talking about percent overshoot, you should start to think, oh, I have this relationship. Here's zeta, and here's percent overshoot, and now I have this curve. And if somebody gave you 10%, we know that's roughly 0.6. If they gave you 5%, well, that's supposed to come down. That's now 0.7. And you might want to have some common values either on your cheat sheet or memorized. I don't care if you memorize these or not. Question? So that's where I was going. Zeta gives you the angle so that you now can see this wedge shape changing in your S-plane. Zeta is related to the theta. Your damping ratio is related to theta. Remember our closed or our S-plane picture, and this distance was zeta omega sub n, and this distance, the hypotenuse, was omega sub n. And if we had this angle, you now know that the cosine of theta is adjacent over hypotenuse. That's zeta omega sub n over omega sub n, or that's zeta. There's your relationship between theta and zeta. And if somebody now gives you a percent overshoot, you can go to figure 5.7, find the zeta. You can now compute the angle theta. That's the inverse cosine of zeta. Common values. If you now had a percent overshoot of 5%, that's now this zeta of 0.7. And what's the inverse cosine of 0.7? What's the cosine of 45 degrees? 0.707. That's close enough, isn't it? So now when somebody says, oh, you need a 4% or a 5% overshoot, now you want your complex poles to have an angle of 45 degrees. Somebody now says, no, I really want a 10% overshoot. And that means now you're going up above where you want to be, 10% beyond, before you settle back down. The zeta for that, we eyeballed to be 0.6. And that angle is now, first cosine of 0.6, you should have all these memorized, right? No, not necessarily, but you will probably by the final in this class. Not that you have to remember those until you retire, but you should remember cosine of 45 is 0.7, right? Draw your 1, 1, 2 triangle or 1, 1 square root of 2 triangle. Do that at night, right on your napkin when you're eating or something. You just want to start drawing triangles. We had the power triangle in 320A, and I was saying, I see a hypotenuse, right? Now you can see a zeta. If somebody talks about percent overshoot, you're seeing a zeta. And that zeta now gives you this angle. So our angle, as the percent overshoot gets bigger, our imaginary component on these poles is getting larger. The angle theta is getting bigger. So that if now somebody says, oh, I want a percent overshoot of 20%, now that's going to be 0.456. Wow, I'm doing 3 significant digits. But then theta, oh, I did 4 on the angle, didn't I? This is now 63 degrees, 62.87 degrees. If you're sketching this, if you're doing it on a piece of paper, you're not going to get this kind of accuracy, 62.87 degrees. You may get lucky if you get between 60 and 65 with your protractor. So at the net, you're laughing. You're going to be bringing in an entire drafting arsenal for this next exam. You're going to have your T-square, your triangles, your scale ruler, your dividers. Everybody knows what a divider is, right? It's not a room divider. It's a... Oh, you guys don't know what a divider is? Okay, look it up on Google. It's a implement that you used to do in drafting class. I'll say used to do because apparently that's not that common anymore. And you transfer dimensions from your scaled ruler with this divider onto your physical paper. Oh, now we just have screens, don't we? So those points, the thing was, if you were in that class and you made the instructor mad, you didn't want him throwing his dividers at you because they're 2 darts coming right at you. And it's a metal instrument usually, and they're metal darts or sticks, pointed needles. It hurt. So if you see any scars, you can just chalk it up. Oh, he must have made his drawing teacher mad. That's not the only. Let's go on. So now we talk about 50%. Why did I get distracted? 50%. What do you think the angle is going to be? In general terms, much bigger or a little bigger than 63, right? So here we calculated this to be 0.22 roughly, and theta now is, let's just say 78 degrees. So if I want a smaller theta, and this means that zeta is getting to 1. Now I'm getting closer to the real line as zeta gets close to 1. When zeta is equal to 1, I'm right on the real axis. When zeta is 0, I'm on the imaginary axis, and we just follow that arc from zeta equals 0, imaginary, all the way to zeta equal 1. That's with our underdamped poles. If this is now, if we want a smaller angle, what's that produce for a percent overshoot? Bigger or smaller percent overshoot? If our angle theta is smaller, now you just have to go up a few lines and notice the trend. Right? This is not rocket science, not yet. We haven't been working with an inverted pendulum today, which is a rocket, isn't it? Your bicycle, you didn't know it was a rocket. It's an inverted pendulum. Rocket's an inverted pendulum, so the next time you get on your bicycle, you're going, I'm a rocket. Just make sure you're wearing your helmet, okay? I want to see you whizzing by me at 9:30 at night or what, some night. Hi, Dr. Tharp. So I scare easily, okay? But luckily I wasn't on the bike path when that happened, was I? I was just in my own world, I guess, thinking about what I was going to talk about in this class the next morning, probably. What did we decide? Smaller theta is smaller percent overshoot. Now we get to have some fun, as if we weren't already. But we get to combine all of these. All three of these design specifications. And if you like to draw, or even color, you might be finding this interesting. So now this is our S-plane. That's the complex S-plane. Here's the real part of S. Here's the imaginary component of S. And now, if we want a particular settling time, which line am I drawing? Vertical, horizontal, or angle? Settling time. Vertical. So now I have this line. This is now my settling time, my sigma, and if I want a smaller t sub s, I want to shift that vertical line to the left. If I now want a peak time, what line am I using? Horizontal. And this is now our omega sub d. And if I want a faster peak time, which way do I shift that horizontal line? I want to put it up, don't I? So that's going up. And now if I have a percent overshoot, the only one left is this line at an angle. And this angle now is theta. This is now the percent overshoot. And if I want less overshoot, how do I sketch this in here without getting it too? Which way do I go? Do I make that angle bigger or smaller if I want less percent overshoot? So now I'm wanting to bring that angle down, aren't I, for less percent overshoot. And where's the sweet spot? Where does Goldilocks want to be? At the intersection of all three of these. If you had all three, if somebody gave you a settling time, a peak time, and a percent overshoot, and you needed to be maybe have a faster settling time than a given amount, a quicker peak time than a given amount, and smaller percent overshoot than a given amount, do you see that you now want to live in this shaded region? And you want your desired dominant poles to be in that shaded region, and it has its twin down below, its reflection. These are coming in complex conjugate pole pairs. So you'll have that one, which is maybe at minus 10 plus and minus j. If I said this is minus 10 plus and minus j10, what's your percent overshoot? Minus 10 plus and minus j10. What angle is that? 45. Cosine of 45? 0.7. What's your percent overshoot? Go to your figure 5.7. You go to 0.7. You intersect and you read over. 5%, isn't it? All right, are we getting this? I'm not even a dinosaur, am I? If you're happy and you know it, clap your hands, all right? Thank you. All right, so one person. We have everyone else is a dinosaur, right? I did see some interesting t-shirts, but let's move on today. Here's our quiz from last time. Now, this was question number 1, and based on what you now know about design specs, hopefully it's a little easier to start reasoning through which pole set or set of poles matches the particular time response behavior. And now we could play Sesame Street, right? Two of these things, I don't know, two of these things are like each other. One of these things just doesn't belong. I didn't watch Sesame Street. I'm too old. I'm a dinosaur. All right. So now, what's the same between these sets of poles? Sigma. So what would we expect to be the same in the time responses if sigma is the same? So we shouldn't worry about the settling time to try to differentiate between these response trajectories. They settle at about the same location and time, don't they? About 4.5. It's hard to see without all my drafting equipment. I'd need my t-square and maybe my triangle to make that accurate to 3 or 4 significant digits. I'm teasing. What's different on these? So they have different omega sub d's, right? They have different imaginary components. So what does that tell you? If I have a different omega sub t, what's going to be different? The peak time. And which one it has a bigger omega sub d? B has a bigger, I'm sorry, I'm cutting my paper and splicing it together, but you don't know what's below, so that's fine, right? So what's this saying about pole set B? If omega sub d is larger in B poles, what does that mean about the time to peak? This is pi over omega sub d, and actually this one is What, can you sort of see omega sub d for the B's? Can you see that? Do you have young eyes? What's the imaginary piece of omega sub d? 2. So now we have to remember that pi is a little larger than 3, 3.14, and you guys probably competed and have pi memorized out to 1,000 significant figures. I don't. Well, 3.14159. That's all I need, okay? And hopefully that's accurate. Does anybody have a calculator? No. So let's move on. This is now about 1.5. Does that look like any of these? Oh. Are we having fun or not? And is that peaking quicker than the number 2 trajectory? So this, just that one difference, distinction, would say that maybe B gets compared with 1 or matched up with 1, right? You could also look at the angle. The angles are different, aren't they? And what's the angle associated with the A set? Well, in terms of actual angle, what's the distance into the left half plane? 1. What's its height above 1? So it's at 45. What's its percent overshoot? 5%. Is trajectory 1 a 5% overshoot? No, because we're at almost 20% overshoot, aren't we, on that one? It's going to 1.2 roughly. So this is sort of saying that B needs to have association with the higher overshoot, which is trajectory 1. Another reason for placing B and 1. So if B is with 1, then A is with 2, and what's the answer? 2, A2B1. So this now says number 2. And I'm sure you all remember what you answered on question 1. Let's go to question 2. Question 2, what's the same here? Omega sub d. So maybe we don't want to worry about the peak time differentiating these time responses, and I can't even hardly see that these are peaking. One of those may not even peak. It may have such a large real part relative to its imaginary part that it may not peak. Its angle may be small. But what is different here? The angle, and we just said percent overshoot may not help us much, even, well, yeah. Maybe I said that, maybe I didn't, maybe I was thinking that. What is maybe going to help us? Settling time. So now these have different sigmas. Or different T sub s's. And which goes with which? Which one is settling more quickly than the other on our time responses? 1. And which pole pair should produce a quicker settling? A. So now this is saying A should be 1 and B should be 2. So this is now A1, B2. Number 1. Right? We're getting the hang of this, maybe. And you'll want to get very quick at this because this is what you need to know. Now, what's the same here with these sets of poles? Anything? Do they have the same sigmas? Do they have the same omega sub d's? Do they have the same angle? Oh, well, we have quite a bit then of information here, right? We should be able to make a pretty quick call. Which one has a bigger angle? And what's that tell you if it has a bigger angle? B has a bigger angle. So that would then mean that what? B is 1. And what's the overshoot of A? Well, its angle is much less than 45, isn't it? Because it has an adjacent of 2 and a opposite of 1. So that's a pretty small angle, and 2 doesn't have any overshoot to speak of, does it? So that's sort of saying that's okay. What about the settling time? Which one of these would settle more quickly, the A set or the B set? A, because it's further into the left half plane. Which of the responses settles quicker? So settling time A is faster implies A 2. So this is now A2 B1, which was number 2. And hopefully you received a 100% on your quiz on Friday. And I looked at most of those over the weekend when you turned in your work, and I agree. So if you missed Friday, you missed some points. Just teasing. We didn't collect anything. Okay. Now where are we? Oh, we want to continue. We want to now start looking at some settling time examples. Now that you're experts with this, let's calculate some settling time. Here's our system. We have our reference input. We have our plant, G of S. We have our output, Y of S. Our feedback dynamics, H, that's 1, so we don't have any H in here. And let's say that we have a reference input is a unit step. So that R of S in the frequency domain is this 1 over S. And here's maybe our error signal. Suppose now that I give you a transfer function, G of S, equaling K0 over tau 0 S plus 1. And now let's pick some values for K0 and T sub 0. Let's say that we want tau sub 0 to be 1 and K sub 0 to be 10. And I want you now to compute the settling time. And I'll give you a few minutes, well, maybe 2, to find T sub S on your own, and then I want you to pair up with somebody and see if you had the same answer or share your answer. Pardon? What? I want the settling time, T sub S. While I'm fixing my computer, what's your question? 2% settling time, yes. So find T sub S. If I don't qualify that, you can assume 2%, but if you want something else, you need to label it. 2% settling time is what? 4 time constants. So I now need you to find T sub S for this example. So find the 2% settling time. All right, you can start sharing. Hopefully you have an answer. Take a minute to share, and then I'll ask for a response. Hmm? Oh. Remember, you have a closed loop system. It's not just based on the G of S. You have cheer 2, right? You need to use the closed loop dynamics to find your settling time. And once you have your closed loop transfer function, what are you trying to find? Maybe that sigma value. The sigma value of your closed loop pole. Hopefully you have this for your closed loop transfer function. K naught over tau naught S plus 1 plus K naught. Now you simply have to find the sigma. And maybe it's not the reciprocal of tau naught, is it? In this case. What's the order of your closed loop system? Is it 0th order? What's the power of S in the denominator, the highest power of S? 1, so it's first order. Now we have a first order. You know the pole has to be real if it's first order. And how do you find the pole if this is your closed loop transfer function? Okay, S is the value that you want the pole, then S has to be the value that causes your denominator to vanish. So you're wanting tau naught S plus 1 plus K naught to equal 0. And tau naught was 1, K naught was 10, S is equal to minus 11. So what's sigma? 11. What's the settling time? 2%. It's 4 tau, which is 4 over sigma, which is 4 over 11. .36 seconds. That's your settling time. We'll pick up at that point on Wednesday.